Three, two, one, and here we go. Our first pre-recorded lecture, and hopefully only pre-recorded lecture, for 317.0 for the fall semester. And I'll try not to make too much noise on my medicine ball here. All right. Maybe you didn't even hear it. You have no idea what I'm talking about. Alright, so plot for this video today is kind of just a quick rundown of functions. So again, we all are probably pretty comfortable with functions as sort of math idea, but we want to talk about them in a bit more formal light here, using our set theoretic framework for how we do mathematics. And again, if you've taken proofs, this is nothing new. But just a quick little rundown of how functions work before we get into a very specific type of function, polynomials, which will be our next topic, which will then, after that, talk about Euclidean space, which is technically built off of functions. Alright, so let's remind ourselves what we are actually talking about. So by a function on a set A, we mean a mechanism that assigns to each element out of the set A unique set, which is denoted as f of A. So function just takes input, gives us output. The set A is called the domain. These are the admissible inputs. A set B, so that f of A belongs to B for all A, is called a codomain. And when we announce a function, we'll write f colon A arrow B to indicate that f takes elements in A and sends them over to B. Nice. All right, so one minor thing to talk about. Another notation before we get into the minutia. Some notation we may write is A, and this is maps to in LaTeX, f of A. So sometimes when functions are announced, we like to use this notation, where we want to talk about where the outputs land. But note how I define a function. We don't really care where they land. We just care about the actual mechanism. You give me a set A and I make an output. So this notation kind of stresses the sort of this gets mapped to that. And you really use this notation especially if you don't really care to be too mindful of the symbol going on here. All right, now a minor point to mention, as I've hinted at here, is that codomain is not a unique thing. You can change it, and you still have the same function. So for an example that gives a really good representation of this principle is the function that takes real numbers and squares them. So x squared obviously is a real number, so this is consider, great spelling. Right, so this function takes inputs from the reals and gives us a real output. Completely valid definition and announcement of a function, but note that we know something about x squared. X squared is always positive. Specifically, it's always greater than or equal to 0, so it hangs out on r plus, and again, our notation for it is this. So this function, we can view it instead of as a function from the reals to all of the reals. We can more efficiently view it as a function from the reals to the non-negative reals. Now, it's worth noting that my viewpoint is that these are the same functions. You're just changing how you view it. Some people are a little bit more sticky about this and will tell you that these two functions are completely different. I'm not of that mindset. I'm of the mindset that the codomain can be changed and you still have the same function. All right, and that being said, let's talk then about when functions are equal. And to me, functions are equal if we have the same domain. Again, no codomain, I don't care if they're the same or not. If the outputs line up for each input, then they're equal. So two functions are equal precisely if f of A is equal to g of A for all A out of A. All right. So let's talk about some things we can do with functions. So in particular, we can take subsets and look at the collection of all outputs with inputs coming from those subsets. This is called the image of the set under our function. And in particular, the collection of all possible outputs is called the range. So note, codomain and range might be different things depending on how you're looking at your function. So note something that f of A has to live in whatever codomain you have, because all of the outputs have to land in that codomain. And in particular, any set that contains the range is then automatically a codomain, and thus you can view your function from the set X to the set D if you want to. Right, so again, this sort of change of codomain thing that we can do, we sort of saw this in action with the x squared example. All right, so something that there is a beautiful litany of is interactions between functions, images, and our set theoretic machinery. So let's get a little sampling of this and show that the image of an intersection is contained in the intersection of the images. So there again, our favorite phrase in math, the x of the y is the y of the x. Here we have the image of an intersection is contained in the intersection of the images. And it's worth noting that equality does not necessarily hold here. All right, so this is a good proof to give us some experience working with images. If you've had it before, great. If you haven't, don't worry, it's good stuff. We will be playing around with images of subspaces on their linear mappings a little later on in the class, so we want to be comfortable with this. But how does the proof of this go? We'll pick an element that lives in the image of the intersection of A and B. That means that element is equal to an output for some input coming from the intersection. All right, well, if you're in the intersection, you're in both sets. So that means x is in A, which then means that f of x is in f of x images, the image of A under f. And a similar argument, and thus you're in the intersection. Nice. And you can see here that if you want to do the reverse, if y lives in the intersection, well, then it's an output for something in A, and it's an output for something in B, but note that the inputs are potentially different. Here, this input came from the intersection. Here, if you were to pick an element here, the inputs would be potentially different, which is why we don't get equality. All right, well, if we have images, then we probably have inverse images, and indeed we do. So note here, this lives in the domain, whereas the image lived in the codomain. So these are the collection of inputs whose outputs land in the set. And a notational tradition that's worth mentioning is that if you do the inverse image of a single set, you drop the brackets and just do curly braces. And also, it's worth noting, notationally speaking, I like closed, I like brackets here. Some people will do parentheses with this. So, for example, I'll do that right here. Some people, and with images as well, rather than having the brackets, they'll have the parentheses. I'm not the biggest fan of that notation. I like my brackets here to indicate, right, that I'm not talking about like the output of my function at an element A or something like that. And inverse image here, so now we have this -1, and this can get a little confusing when we talk about inverse functions, and you may have encountered dealing with notational issues in inverse functions with arcsine and arccosine. So some people, instead of putting a -1 up here, will actually, check this out, they will put, trying to get it to freaking load, there it is. They will actually do this for their inverse images. They'll put a arrow. And notationally, right, you can kind of think it's taking A and pulling it back into the domain. Kind of interesting. But I haven't officially, formally adapted that notation in my life. I'm too used to the -1, so that's what we're going to use. All right. Again, it's worth noting. Yeah. So, again, we can prove a whole bunch of facts about how inverse images interact with sets. And for a quick proof, the inverse image of a set difference is the set difference of the inverse images. So if we pick an element in the inverse image of B minus A, that means f of x lands in B minus A, which means f of x lands in B and f of x does not land in A. So that means x has to be in the inverse image of B, and x can't be in the inverse image of A, because fx did not land in A. So we're in this set and not in that set, which means you're in the set difference. So we get subset in that direction, and the reverse direction is basically just read the proof backwards, and it works. There we go. So here you see proofs with inverse images usually work a little bit better than proofs with images in general. And depending on where you go in your math life, you will learn that inverse images actually are a very powerful math tool and help us actually characterize continuous functions. So there's a reason inverse images end up being kind of a very powerful math tool and end up being very useful when you're studying things. And generally speaking, proofs with inverse images they just work so much better. All right. So what are some other things we can do with functions? So images and inverse images might be a new one for you, but composition definitely isn't. So composing two functions is something that we do all of the time in mathematics. You put x squared plus 1 inside of the square root. You put log inside of your cosine. There are all sorts of things like that occur naturally in mathematics. Putting a function inside of a function is something we do, and we can formally describe that as the composition. Okay, and there are, again, involving images and set theoretic machinery. There's all sorts of theorems you can prove with compositions, so let's get one more proof here to kind of, again, get comfortable with using these things, and as we'll see, the proofs of this stuff is pretty straightforward. So suppose x is in the inverse image of the set B under the composition of f and g. That means g of f of x, which is g composed with f, evaluated at x, that lives in B. That means f of x is in the inverse image of g under B, which then means that x is in the inverse image of f under the inverse image of g. So there, note I'm simply just unraveling our definitions. And then going backwards is essentially just read the proof backwards again. So here we see once more inverse images behaving quite nicely. It's worth noting that there is a similar result for images that can be proven. But this one's interesting because here we see I've got my g composed with f, and then I have my minus sign appearing. Ooh, look, it flipped the order of them. Oh, that's really interesting. I wonder if there's like some super deep abstract algebra thing going on here. Maybe we'll see this with the product of two matrices and their inverse. We'll find out, I guess. All right. So another function technique that we will encounter is restricting, which is kind of an interesting thing because it basically just says take your mapping and ignore some inputs. And the notation that I like to use for this is you take your function, you put a bar, and then subscript the set we're restricting to. So we will see this maneuver show up later on when we have linear mappings, and we're going to restrict their inputs to certain subspaces, like maybe fundamental subspaces of matrices. And there's some things you can prove here. So note here what I'm doing is each time we're introducing this sort of new function technique, we're seeing how it interacts with some basic set theoretic tools, just to, again, get us comfortable working with these things, and just, proofs are fun. We like doing proofs. So this one's interesting because this tells us how we can relate restrictions to the original function. And again, here we see inverse images behaving quite nicely. Right, so if you are in the inverse image of the set B under the restriction mapping, well then the output of that lands in B, but the output of this, by definition, is just whatever the output of F is. So that means X is in the inverse image of B, and because X was in the inverse image of the restriction, it's got to be in the domain of that, which means it's also an X. And there you go, it's then in the intersection, and then, again, our favorite phrase, the reverse inclusion is proven similarly. Just read the proof backwards and you're good to go. Alright, cool. Alright, now, what's some other function maneuvers we can do? One is gluing them together. In particular, if I have a function defined from A to C and B to D, and I know my functions coincide with each other on the intersection, then I can form the piecewise defined function on the union, where given anything in A, we output F, and given anything in B, we output G. And note here, in order to keep this nice and well defined, any points where we overlap, the functions need to agree. Right? If there is a point in the intersection where f and g are different, then this is an invalid function construction because there would be a point where there's two possible outputs, and we don't allow that for functions. So piecewise functions are ones you definitely ran into in your calculus days. These are the favorites for creating weird discontinuous things or making fun problems where find the value where this thing is continuous. Now, it's worth noting that when we do announce these, so generally speaking, you can write it like this, but usually how these arise is the set A is derived from set builder notation, so formed using a proposition, and the set B is the points where it doesn't hold. So I want to say proposition, not propositions. I'm changing that typo, but I haven't changed the other ones, I've noticed. So another way these are usually announced is you've got your f of x, where that's some proposition regarding x, and then g of x is when this doesn't happen. And note there would be no overlap between those sets there, so you don't have to worry about it. All right, so we'll see these in effect here and there. So I was debating on proving something with this to get some feel for it, but like I said, we'll see these encountered. So let's talk about some other function constructions. So here's a common one. Given a set and another set C, I could talk about the function that is identically the set C. So this is the function that's just constantly spitting out C for any input you give me in A. Now, I have never seen a good notation for this, so typically people just will use the letter for the set and go like, oh, this is the function. But we may use some other notation if the distinction between the set and the function that's identical to that set is unclear. So, for example, the function that's constantly 0 from the real numbers to the reals. Constant functions are a very important part of mathematics, so we want probably a symbol for this, and one that I've seen a lot of people use is bold. So they'll bold it and go, you know what I'm talking about. But as we see as we'll go forward, we're going to bold things for other reasons, and it's very difficult to have a consistent notation across the board here. So when it comes to functions that are identically identically constant to something, we just sort of on an ad hoc basis will announce what symbols or whatever represent them. Now, I've been saying the word constant, but it's worth noting that the precise definition for a function to be constant is that the outputs are always equal for any two inputs. And note that if the domain is non-empty, that means you have to be identically equal to some set on that domain. And note, this is kind of implying that I can have a function whose domain is empty. Because I can. Because the empty set will vacuously satisfy the definition of a function there, because all inputs have an output associated with them, because there are no inputs. Good stuff. Classic. Alright. Neat. Alright, another function that we will frequently encounter is the identity, which is the give me inputs, don't do anything, just leave them alone. Notationally speaking, I like to use I sub A for this. Some people do a ID, so you'll see, so for example, I'll create that here in a second. So some people will use this, like IDA, to indicate it. I like just using a capital I. Again, there's not a lot of standard notation here with this stuff. Just pick something and stick with it. I love always like using just capital I for this for a variety of reasons. And whenever the set A is obvious, you'll just write I, and you'll know what you're talking about. Now, an interesting thing to do with the identity function is to take a set that contains A. Then the identity mapping can be viewed as a mapping from A to B. And in this case, we call it the inclusion mapping, and some people like to announce this with this hooked arrow, which I always thought was a cool-looking symbol. But the hooked arrow gets used for embeddings, and we'll talk a little bit more about that. In fact, we'll revisit the inclusion map in a second here later on. But that's just a neat thing, and you'll see some people write this like that. So again, remember, you can change your codomain. You can view your function as a mapping from a domain to any set where the outputs are landing in those sets, and any set B that contains A, well, all these outputs certainly live there. So, all right. So the identity function, we'll see it frequently throughout our math journey. So. All right, now, following the footsteps there, let's talk about some properties functions can have, and the all-time classics are one-to-one, and since we're adults, we're going to use the word injective for that, but this is functions that pass the horizontal line test, meaning that if two outputs line up, then their inputs must have been equal. And onto, meaning that the codomain we're looking at has a input that matches it. So note, with my viewpoint of every function can be viewed as a function to its codomain, to its range. This means that technically every function can be viewed as a surjective one, because if you just change its codomain to its range, then you're automatically surject. And like I said, some people are not a big fan of this whole you can change your codomain, because then all of a sudden it has a property that it didn't have before. So how is it the same function? Yeah. They're right. This is a stylistic thing, but I'm of the viewpoint that surjectivity is a property that you can or cannot possess, depending on if you want to view it as not. Caveat. All right, so these together are going to give us something that we've kind of already discussed, and that's inverses. So let's say we have a function, and we have an element y living in our codomain. If we are surjective, then this inverse image is non-empty. And if you throw in injectivity, then in fact, this has to be a singleton, meaning there is a unique element that it is equal to. There is only one thing in the set, and it's x. All right, and so let's do the proof of this. Give us a little comfort. All right. So by hypothesis, we're surjective. So if you have a y in the codomain, then there is an x that hits it. And so that means f of x lands in that set, so x must be in the inverse image of that set. Okay. Oh, and I didn't mention it before when we talked about these. The inverse image of a singleton, these are sometimes called fibers. Which that's when you're doing cool stuff. I'm looking at fibers. All right, cool. All right, so there you go. It's not empty. Now, point two. Let's say we throw an injective. So we know it's not empty. So that means there's something in there. And note that inverse images live in the domain, so x must be in x. So let's say you've got something else that lives in it. Well, if you live in the inverse image of the singleton, that means your output lands in there, which means your output's equal to y. But x was in that set, so its output hits y, which means f of x is equal to f of z. And by our hypothesis of injective, that means they're equal. So that means that the only thing in this set is the single element x. And we already have it's the only element in the set, so the uniqueness of it is trivial. All right, so a function that is both injective and surjective, so a function that's both one-to-one and onto, is called a bijection. And by the previous proposition, that means that for every element in the codomain, there is a unique input in the domain where we have this relationship. And that gives us access to a function, right? Because given an input, there's a unique output. So there is a function g that satisfies that. And note that that would mean that f of g of y has to coincide with y following this, and then g applied to f of x would have to equal x. And oh hey, f composed with g is the identity on y, and g composed with f is the identity on x. Ooh. So this function g is called the inverse, and it can be proven to be unique. And it is, and by unique, I mean it uniquely satisfies this property right there. And as I've noted, inverse functions are unfortunately denoted as f to the -1, which kind of conflicts with another use of f to the -1, which would be 1 over f. You just need to be careful about what thing you're announcing. And normally you get around that with fancy notation, right? So for example, the inverse of tangent is arctangent. Some people do write it as tangent to the -1, but that's, that 1 over tangent, of course, is cotangent. So, all right. So, functions can also be announced using indexing and notation. So by this I mean we'll write this, and this means that there is a function whose domain is this set here, which is sometimes called the indexing set. This is the codomain, and the function's output is the a sub alpha. So this is basically saying I've got a mechanism of assigning to each element out of lambda some thing a lambda, and they all live in x. And when this mapping is injective, then we call it a distinct list. So indexing sets that are frequently used are the following sets. So the set of integers from n to m, which formally is a set, but more conventionally we write as follows. And all of the integers greater than a particular integer, which is conventionally written as follows. So, right, we've kind of already mentioned these sets before. And as is tradition, anything that's indexed with these things are written in these styles. So a list of elements starting at n, or a list of elements starting at n going on indefinitely. So these sort of index sets like these are going to play a pretty big role in a lot of the stuff we do, especially when we're talking about bases for vector spaces. We're going to generally run into these. And something else that we're going to do with index sets is a reindex, which means I can take a list of things that start from 1 to n, but then I can shift it, and instead of starting at 1, I can start at negative 1. So for example, here, y of negative 1, you'd plug the negative 1 in here and get 1. N minus 2, plug that in, the 2's cancel, you get x of n. So, right, it doesn't matter where you start indexing, you can move it around to wherever you want. We've kind of already mentioned this, but typically we'll start at 1 or we'll start at 0 depending on the context. Index sets can be glued together, so if you have a list of elements x1 to xn and a list of elements y1 to ym, we can glue them together and make a list of elements from 1 to n plus m, where the first n terms are x and the next m terms are the y terms. So note formally this is how you'd write it out. Note that z sub n plus 1 would be... I need k minus y, not k minus n, sorry. Not the other way around. Because I was just about to go, then you have an index of negative 1. And oof, I'm a goof, that's not right. There you go, that's correct now. And another maneuver that we can do, and this one we're not going to do too frequently, but it's worth mentioning, is you can stitch index sets together and have them alternate. So you have an x1, then y1, x2, then y2, and so, for example, this gives you a formula for that. And here again, we see the piecewise things being used. Again, a very common maneuver in mathematics. All right, so a very powerful tool for indexing is counting how many elements you have in your set. So, for example, a set is said to be finite if it's empty, or I can find a finite list of things that line up with it. Now, note, right, I said this is a finite list because I'm using our intuitive representation of the idea of finite, but note, formally speaking, right, I'm just saying there's a function whose domain is the natural numbers from 1 to some n, and the output of that, the range of that, coincides with our set x. That's what we mean by being finite. Infinite if you fail to be finite. Countable if you're some indexing where the indexing is all of the natural numbers. But note that this does allow for infinite repetition. So if you want this and you want this to be distinct, that would then give you something that could not be finite, and that would give us the countably infinite. So you're infinite and countable, and uncountable if you fail to be countable. Now, classically, our sets of the natural numbers, the whole numbers, the integers, and the rationals, these can all be shown to be countably infinite. We're not going to take the time to prove this. It takes not a lot of work, but a little bit of work. We kind of, I don't want to say we don't have the time for it, but that goes a little bit beyond what we want to do in this class, but it's worth mentioning. Whereas the real numbers and the complex numbers are uncountable. The uncountability of the real line was established by Cantor, and there are quite a few arguments to prove it that are all pretty neat. And again, we don't need to get too into that for our course, but it's worth mentioning this stuff. And it's also worth mentioning a very famous problem in mathematics. So the size of sets can be compared using injections. So if there's an injection from x to y, that means there's a copy of x in y, because for every element in x, there's an element in y that it uniquely maps to. And we write this instance as the absolute value of x is less than or equal to the absolute value of y. And we make it strict if there's an injection, but there's no surjection. So I can't form a bijection between the two. It can be shown that that there is an injection from the naturals to the reals, but there's no surjection from them. That's this uncountableness here. And this is like asking, well, we have an inequality that we have on the real line, so you would hope that there would be sort of like a analogous thing there. And we know something about the inequality on the real line is that there's stuff in between things. So a mathematician by the name of Cantor is, I already mentioned him, is the one who sort of developed all this stuff, and he hit this, and he went, well, all right, can you find a set hanging out between the two? And the answer is, depends. Do you want there to be one, or do you not want there to be one? You get to choose. This is called the continuum hypothesis, and it turns out that our usual rules for set theory cannot decide if there is such a set or not. So you get to. Do you want it or do you not? That's kind of an interesting thing. So for the lore enthusiasts, check out the continuum hypothesis and look into that. It's good times. All right, and let's wrap things up here by talking about our favorite math technique, recursion and indexing. So something that we can do is recursively create summations. So the sigma notation for sums we've ran into in our math life, and it tells me how I can add up a list of numbers. And the way this is defined is recursive. You tell me that if I want to add up the first thing, it's literally just the first thing by itself. And then if I want the nth thing, I take the n minus 1 thing and add the nth thing to it. Or equivalently, the n plus 1, I can tell you the nth thing. However you want to do. So with this in hand, we now know how to recursively work with summations, and so then we can prove a incredibly famous summation formula, the sum of the first n numbers, which is n times n plus 1 all over 2. Very famous result, and since we used recursion to define these things, that means we're going to use induction in the proof. So, base case. Well, plug in 1. There you go, it works. Now, suppose it works for some n, I'll show it works for n plus 1. So, we look at n plus 1, we know that you can peel off the n plus 1 term like this. The induction hypothesis tells me that this is equal to that. Alright, well I'm adding this. I want to match the denominator, so I bring in the 2, I combine, I factor out my n plus 1, and then I note that n plus 2 is really n plus 1 plus 1, so here we see the result is true for n plus 1. So, nailed the base case, assumed it worked for n, and then we showed it worked for n plus 1, so by induction it works for every natural number. Beautiful. And hey, that concludes our little crash course here on how functions work. Pretty exciting. So next time I see you in person, we will talk about a very famous kind of function, the polynomials. Ooh, a bird that does not eat.